Hello again. This is Math 2134 coming to you from the College of DuPage, and the title of this lecture is Integrals as Areas. Make sure that you are an active learner while watching this video. By way of introduction, in the same way that the geometric interpretation of a derivative, which proved to be a very important limit, was useful, and was in fact, as a review, the derivative is the slope of the tangent line to a curve. We learn in this lecture that the definite integral also has a geometric interpretation. The definite integral is the net area under a curve. Now, we haven't really defined what the definite integral is yet. We've talked about antiderivatives, and we've talked about indefinite integrals. But before defining the definite integral, which will prove to be another very important limit, we consider approximations to areas under curves called Riemann sums. Integral calculus studies the accumulation of units as the input variable increases. For example, suppose a jogger maintains a constant velocity of 5 miles per hour. As she runs, she accumulates distance. After 1 hour, she has run 5 miles. Between the first hour and the second hour, she also runs another 5 miles. And so that for the first 2 hours, she has accumulated a distance of 10 miles. We can view accumulations graphically, as shown in the final example. So we have Emma, who drives her motor scooter at 15 miles per hour for an extended period of time, a constant speed of 15 miles per hour. So how far has she traveled after 1 hour? Well, that's going to be 15 miles per hour times 1 hour is going to be 15 miles. Now, you see, if we're graphing her velocity along here, her velocity is and this is the y-axis, is the velocity. So velocity as a function of t is 15. It is constant going forward. But you see, the answer to this was the area that she got under the curve going from 0 to 1 is also 1 times 15, or 15. B, how far has she traveled between the first and second hour? Well, here is a snapshot of between the first and second hour. And again, the rectangle is 15 high and 1 wide, and that's 15 miles that she's traveled during the second hour, because she's a constant, 15 miles per hour, but it's also the area of this rectangle. In C, how far has she traveled cumulatively over the first 2 hours? Well, you see, it's the addition of this rectangle and this rectangle, or it's this rectangle. And so you see this side is 2. The height is still 15, so the answer is 30. And there it's 30 miles that she's traveled. Part D, what function f of t gives Emma's total distance, traveled after t hours? Well, you can make charts on that, but what you see is that it's always going to be the area under this curve, and these are the values 1 through 4. So the accumulated distance under suggests that this function gives her total distance traveled in miles after t hours, because if you take t to be 1, 2, 3, or 4, this gives you that equation. And note that 15t is an antiderivative of 15, because you see the constant just sits there, and you can think of this as 15 times t to the 0. Add 1 to the exponent and divide by the new exponent, and you have 15t. Let's talk about another example, and we're going to have to broaden our geometric scope. Here was the rectangle again, and the area under the rectangle is always going to be base times height, or length times width. But we're also going to talk about more complicated functions, and so we'll talk about the area of a triangle. And the area of a triangle is 1/2 the base times the height. Now notice that the base is a distance along the bottom, but the height is the perpendicular drawn to that base from the opposite vertex. So anyway, keep those formulas in mind. We will use them, and we'll talk about example 2, which is drawn from the physical science, and this is distance as an area. So suppose a toy drone flies in a straight line, and its velocity t seconds after takeoff is given by v of t equals 2t. So you see it starts out at the very beginning going 0, but then it starts going faster and faster. So it's going 2, and this is meters per second, and it goes, so it's going faster and faster and faster because its velocity is growing at 2t. Okay, find the distance the drone has flown after 1 second. Well, after 1 second, then, you see it's going to be the area under the curve is going to be this. Now, the area is 1. You can say, well, it starts at 0 and it's accelerating and it goes up to 2. That means its average velocity is 1. So anyway, this area, for many reasons, is going to be the area is equal to 1. It's the area of the under the triangle. B, find the distance the drone has flown between t equal 1 and t equal 2 seconds. Well, it's this picture, and the distance here was 1, but then we have to calculate this. Now, there's really two pieces. There is a triangle on top, and there's a rectangle on the bottom. Now, the area is 3, because this one is 1 times 2 is 2, but this is going to be 1 times 2, 1/2 the base times the height, so this is 1. So the area of the triangle is 1, this is 2, so the total area is 3. For part C, find the cumulative distance the drone has flown over the first 2 seconds. Well, you basically are adding this area to this area, but if you think about that for a while, it's going to be still the area under the curve. And so what you do is you're adding those areas together, and you get that this area is 4. Now notice that the area of this is 4 because the base is 2, and the height is 4, and the area is 1/2 the base times the height, or it's 1 times 4, so the area is 4. Now if we take these two examples 1 and 2 in this section, it suggests a pattern. If you have a function that is flat, f of x equal a constant, then the area accumulated as you go across that is going to be k times x. And if you have a graph of a function y equals mx, which is a line that goes through 0, 0, of slope m, then the area of this is going to be 1/2 mx squared. You see m is where you get to up here, so the height is mx, the base is x, but it's the area that has a formula 1/2 the base times the height, so it's a 1/2, so this is 1/2 mx squared. And notice that m is a constant, so 1/2 mx squared is the antiderivative of mx, which is the equation of this line. Because m is a constant, x is the variable. You add 1 to the exponent and divide by the new exponent. So you add 1 to the exponent, you get squared divided by 2, which was the new exponent, and you have this as the area. Let's do another example. This has to do with business and total cost. So we have the skateboard company has the following marginal cost function for producing skateboards. Now you remember marginal cost means the derivative. So C prime of x is equal to, and you see that the price goes down the more you make. The marginal cost changes, and in fact it goes down the more you make. So we have this. And C prime is the cost per skateboard, per unit skateboard, which is what the marginal cost means. Find the total cost in producing 150. Now, when you are making 150, it's your total cost, so that is going to be your cost times how many you make. So you see the first 50 are going to cost $40 each. The next 75, going from 50 to 125, are going to cost 30 each. And the last 25 that you make, if you're making a total of 150, are going to cost 25. So if you look at the picture, you will see that the first 50 cost 40, and 50 times 40 is going to be the area of this. The next 75 is going to be the area under this, and the last 25 are going to be this. So you see, the total cost of producing 150 skateboards is the sum of these three areas, and if you add those areas up, you get $4,875. So this motivates an idea, and the idea is, gee, if you even had a more complicated function that varied this way, you can use rectangles to approximate the area under the graph, as long as it's as if it is continuous, and this certainly is a continuous function. So what we'll do is we'll say, well, we're just going to take this value and we'll make this rectangle, and that is almost the area under the curve. It's a little less. And then for these values of the function, when we substitute those values in, we can see that if I make this area, that's a little bit of an overestimation. This one is an overestimation, and this one is an underestimation. Okay, so what we did is we took the area formed by those rectangles, and we're using that to approximate the area of the curve. Now notice what we do here is we start by dividing the interval, which runs from A to B, into 4 equal sub-intervals. And since they're equal, the change in x, the delta x, is b minus a over 4. The heights of the rectangles are, and we just pick these values, these are the left-hand endpoints. X1 is a, and x, and that would actually be x5 as being that, but x4 is the, just down from b. And so we slice this into 4 pieces, a minus b, so actually it's b minus a over 4. And these are the heights of the rectangle. So the area of the rectangles is going to be f of x1 times delta x plus f of x2 times delta x plus f of x3 times delta x plus f of x4 times delta x. This is what is called a Riemann sum after the great mathematician Bernhard Riemann. And we can denote this sum with the summation sign or sigma notation. And this is the Greek letter sigma. So you see, this is an expanded version of writing this. What we do is we start and we're saying, okay, we're going to add them up. Let I be 1. When I is equal to 1, we get f of x1 times delta x. That's this part. And then we say, now we'll take I to be 2. This is f of x2 times delta x. And then we say let I equal 3. This is f of x3 times delta x. And 4, you get this. So you see, this is what this area is. And the way we read this is the sum of the product f of xi times delta x from I equal 1 to I equal 4. And so we can substitute those numbers in and actually do a calculation. Let's do some examples of this. So we want to write this in expanded notation, not the concise summation notation. So when I is equal to 1, we get h1 delta x. Delta x does not depend on I, it is a constant. When I is 2, you get this one. When I is 3, you get this one. When I is 4, you get this one. And when I is 5, you get this one. So that is how we write this in expanded form. We still haven't done this with numbers yet, but we're going to change that right now. And here what we're looking at is the graph of a quarter circle. Now, and this is a quarter circle of radius 2 that is centered at 0, 0. So you see that is x squared plus y squared is equal to 4 is the equation of the circle. But if we solve that for just the top half of the circle, it's y is equal to the square root of 4 minus x squared. So this is a quarter of the circle, centered at 0, 0, and of radius 2. And now what we're going to do is we're going to calculate some Riemann sums. Okay, so we're going to say, let's divide it into 4 subintervals. So we slice it into 4 subintervals. Now, if you go from 0 to 2 and slice it into 4 equal pieces, you find that delta x is equal to 2 minus 0 over 4, or 1/2. So delta x is always 1/2. And then we are going to be using the left endpoints, and so we're going to say the summation as I equal 1 to 4 of f of xi is going to be, and so you see we're going to say, well, what is f at 0? And it is 2. So the height is 2, but each of these is 1/2. So this is f of 0 times 1/2. This is f of 1/2, which is this one right here, times 1/2, f of 1, which is this one, times 1/2, plus f of 3/2, which is this one, times 1/2. Make sure you understand this. The 1/2 is common, so I can factor it out, and then I can plug these numbers into my equation up here to figure out what they are. Now, in this case, we use a calculator because it's quite a calculation, but this is going to be approximately equal to, because we're using the calculator, 1/2, that is 2, plus this number, plus this number, plus this number. Again, we're plugging in here to get our answer. You add them all up and multiply by 1/2, and you get is 3, almost 3.5. So the area is approximately this. Notice you can tell from the picture that was an overestimate. So this approximation is greater than the actual area of the quarter circle. Let's increase the number of subintervals. This time, let's slice the interval from 0 to 2 into 8 subintervals of equal width. Then delta x is equal to 2 minus 0 divided by 8, or 1/4. You see we're making these intervals smaller. And so then what we're going to do is we're going to have these endpoints here. So it's going to go 0, 1/4, then it's 1/2, 3/4. You see we're adding a fourth each time, and we end up at 2. So now what we're doing is we are going to calculate this Riemann sum. Again, it's going to be an overestimate. But what happens is, and delta x is always 1/4, as we talked about up here. So we just plug in these values, f of 0, into our equation, the square root of 4 minus x squared again, and we get this is the sum of the areas of the rectangles. But now we have many more rectangles. We do the calculation as we did before, factoring out that. We find that this is approximately 3.3982. Now this is still an overestimate, but you see it is closer to what the actual area is. Still an overestimate, but the other one was broader. The approximation is still greater than the actual area, but the difference is less than when we used 4 subintervals. Now, what is the actual answer? Well, this is a quarter circle, and the radius is 2. So the area of a circle is pi, that irrational number, and this is what it is to those many decimal points. Dot, dot, dot means it never terminates, never repeats. So it's going to be pi, that number, times the radius squared. So you see area is pi times 2 whole squared is 4 pi. And if you think about what 4 pi is, it's close to, well, the area is 4 pi, and that's what it is exactly. And if you figure out what that is, you get an answer close to, oh, and you have to take 1/4 of that, and so actually this is very close to pi, because if you divide 4 pi by 1/4, because this is 1/4 of the circle, you'll get the actual area is this. So you see we were approximating the area and getting closer and closer. Let's look at another example. Let's use 5 subintervals. Actually, I have this on the next page. Use 5 subintervals to approximate the actual area under the graph of f of x equal, and this is 0.1 x cubed minus, this is 2.3 x squared, this is plus 12x plus 25. And we're going to divide this into 5. Now you see we're going from 1 to 16. So, since we're going from 1 to 16, delta x is 16 minus 1 divided by 5 is 3. So each of these bases is going to be 3. And then what we do is we take this point to estimate the height, 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 and this point to estimate the height. Now I don't know if this is an overestimate or an underestimate. Here was an underestimate. We were over, and this is an underestimate. So, but our approximate area is, again, we add up the area of the rectangle. So it's f of 1 times 3, f of 4 times 3, f of 7 times 3, f of 10 times 3, and f of 13 times 3. We do the arithmetic, and we get 405. Finally, we're going to define the definite integral. The key concept is that the more subintervals we use, the more accurate the approximation of area becomes, at least for these examples. As the number of subdivisions n increases, the width of each rectangle, delta x, decreases. So if n goes to infinity, then the size of delta x approaches 0, and the Riemann sum approaches the exact area under the curve. So the exact area under the graph of a continuous function, y equal f of x, over an interval, ab, is given by what we call a definite integral, and here is the definition. So if f of x is continuous and non-negative over an interval, ab, a definite integral is the limit as n goes to infinity, or, as we discussed above, delta x goes to 0, of the Riemann sum of the areas of the rectangles under the graph of y equal f of x over ab. So the exact area is the limit as delta x goes to 0. Calculus is the study of limits. So the exact area is the limit as delta x goes to 0 of the summation I equal 1 to n of f of xi times delta x. And this xi can be any number within that tiny subinterval. And the way we read this is the integral from a to b. In fact, this is the definite integral from a to b f of x dx. So you see the exact area under a continuous function, y equals f of x from a to b, a finite interval, is called the definite integral from a to b of f of x dx. And notice that in the limit, when delta x goes to 0, this is our function, but the delta x becomes what we call dx, and that's the differential that we talked about before. I think that's what they say here. Delta x becomes dx, and we use the integral sign. And the integral endpoints, a and b, are placed at the top and bottom of the integral sign. That makes it a definite integral instead of an indefinite integral. Okay, now let's then suppose in example 7 we're asked to find the value of the definite integral from 0 to 2 of 3x plus 2 dx. Well, let's consider the graph of 3x plus 2. Now this is a line that has a y-intercept of 0, 2, and the slope is 3. So this is 3x plus 2. So I'm going to graph y equals f of x equal 3x plus 2. It has an intercept at 0, 2, and the slope is 3, and it looks like that. And that's what it means when I get to 2, I can substitute 2 in here, and I'm going to get 2, 8 is this point up here. And we want to know the area under that curve, between that curve and the x-axis. Well, we really have to cut this into two pieces First we have a rectangle, and then we have a triangle. So the area of the rectangle is 2 times 2, and this is 1/2 the base times the height, and we're going to see that that is going to be 1/2. Again, it is 2, and this height is 6 because you go from 2 to 8, and that makes that 6. So 1/2 times 2 times 6 is 6. We add those two numbers together, 6 and 4, and we get 10. In closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now, more than ever, take care of yourself and each other. God bless you all.